Assalamu alaikum wa rahmatullahi wa barakatuh. Till now, the chapters that we have completed are we started with electric charges and fields. After that, we moved on to electrostatic potential. And capacitance. These two chapters, electric charge and fields and electrostatic potential and capacitance, these two comprise a single unit called electrostatics. Next, we moved on to third chapter, that was current electricity. After current electricity, we moved on to another chapter, that was moving charge and magnetism. And at last, we finished the chapter magnetism and matter. Fine. These are the 5 chapters that we have finished till now. Let me remind all of you that we defined electrostatics as that part of physics when we study physics of charge at rest. Here charge was supposed to be at rest. Then we studied whenever the charges are in motion. You call that as current electricity. Then we observed one more effect of this electric current. Initially, when charges are at rest, that's electrostatics. We studied physics, like what's the force exerted between two charged bodies, what is the electric field. Similarly, what is the potential of a charged body, how much charge is capacitance stored in a capacitor. We finished those things. Then we moved on to current electricity. In current electricity, we assumed that charges are in motion. By charge in motion, what we mean is, by charge in motion, we basically mean charge is flowing. Fine? Charges are flowing. Then we studied one more thing. We discussed this in class, that it was found that whenever charges are in motion, it was found that when a current carrying wire was placed near a bar magnet, or whenever a small magnetic compass needle was brought near a current carrying wire, it got deflected. And we already know this thing, that only a magnet can deflect a magnet. If a current carrying wire is able to deflect a magnet, that means we had a current carrying wire here, and what we did, we placed a small magnetic compass needle in the space nearby to the current carrying wire, carrying current I. Whenever this current I flows through this wire, this magnetic compass got deflected, either here or either here, depends upon direction of current. So we concluded that wherever you have a current carrying wire behaves as a magnet, and it produces a magnetic field. When that magnetic field interacts with the magnetic compass needle, so this magnetic compass needle is deflected. Fine. And then finally what we studied about the permanent magnets. Basically, in this permanent magnetism, we studied about the magnetic field of the earth, how much is magnetic field of Earth, what is the magnetic dipole, how does a bar magnet differ from a magnetic solenoid. We studied all those things. The next chapter that we are going to study now, we are going to start a new chapter, that is chapter number 6. This chapter number 6 that we are going to start is electromagnetic induction. Today I will give you a brief overview of what this electromagnetic induction means. What does this basically mean? Look here. All of you are aware that whenever charges are at rest, they produce electric fields. They produce electric field, where we defined as electric field as a region around the charge in which its influence can be felt. Next thing that we studied is whenever this charge is in motion, say with velocity v, in addition to producing an electric field E, it also produces a magnetic field B. I hope you remember this. You can refer to your previous class lecture notes. Where this magnetic field B produced by this charge Q moving with velocity V was equal to, okay, leave that for time being. So this moving charge produces a magnetic field. Fine. Or whenever a current I flows through a wire, it produces a magnetic field B around this wire. We have discussed the shape of the magnetic field because of straight wire, because of solenoid, because of circular loop. We have already discussed them in the class. The thing here is, this number 2 and number 3, they both are basically the same. There's no difference between this and this. Both of them are same. Why? Because we already know when a charge Q is moving with velocity V, it constitutes a current. So you can say whenever a charge is moving with velocity V, it produces a magnetic field, or alternately you can say whenever a current I flows through a wire, it produces a magnetic field. This is one and the same thing. There's no difference between the two. Fine? Both of them are same. Okay. Now I have to introduce you to a new concept today. The thing is, it was felt that if a current carrying wire can produce a magnetic field, or in other words we can say, if a charge moving with velocity v can produce a magnetic field, can magnetic field produce electric current? I will repeat this. Since current I flowing through a wire can create a magnetic field B around the wire, the question that was asked that can the magnetic field B produce a current in a wire? Can it produce a current in a wire? Alternately, we can ask this question in another way as well. Since electric fields can produce magnetic fields, the question was, can magnetic field produce an electric field, or can magnetic field produce an electric current? The answer to this question was yes. Electric fields do produce magnetic fields Similarly, magnetic fields can produce electric currents, or magnetic fields can produce electric voltage, or magnetic fields can produce EMFs. The answer to this question was yes. Magnetic fields do produce electricity, but there are some conditions. The condition here is changing magnetic fields produce electric current, or to be more precise, in fact to be more general, we can say produce EMF. Fine. So the question that we asked today is, can magnetic fields produce EMF? The answer to this question is yes. Magnetic fields do produce electric current, or magnetic fields do produce EMF, but not magnetic fields, the changing magnetic fields will produce. So you should have to remember this thing. I will come to this, why changing, not magnetic field. The changing magnetic fields produce EMF. Fine. So who was the first person to put forward this? The answer to this question was provided by the experiments of Michael Faraday. What we commonly refer to as Faradays Experiments of electromagnetic induction. There are three experiments that were conducted by Michael Faraday. What are the experiments? Experiment number 1. In experiment number 1, what Michael Faraday did, he used a coil. And to this coil, he connected a galvanometer. You are familiar with galvanometer. This is a device used to detect the current. And what else he did? He took a bar magnet. You tell me normally, if this bar magnet is not here, what will be current flowing through this wire? It will be zero. Why? Because there is no source, no battery, no voltage source connected across the wire. There will be zero current flowing through the galvanometer. It will show zero deflection. What was found that when Faraday's experiment showed that when Faraday moved this magnet towards the coil, whenever this bar magnet was pushed towards the coil, this galvanometer showed deflection. Next, what he did, this bar magnet was not pushed towards the coil, it was pulled away from the coil in this direction. Again, the galvanometer showed deflection. In either case, galvanometer showed deflection. Whenever this was pushed towards the coil, whenever this was pulled away from the coil, This galvanometer showed deflection. This was the first experiment. Second experiment. In second experiment, what was done is Faraday took a coil, connected a galvanometer across it, took another coil here, connected a battery over here. Now in this coil, let's call this as coil A, let's call this as coil B. In coil number B, we have connected a voltage source V in this coil and resistance R. Will some current flow in this coil or not? Definitely a current will flow because you have connected a voltage source and the circuit is closed. So a current I will flow in the circuit where current I will be equal to voltage V divided by resistance R. Voltage V divided by resistance R. This current is flowing through this wire. Now we already know from the physics that we have studied, whenever current flows through a coil, that coil behaves as a magnet. Now what Faraday did, when Faraday pushed this coil towards this coil A, that means Faraday pushed coil B towards coil A. Again this galvanometer showed deflection. Then he pulled this coil B away from coil A. Again this galvanometer showed deflection. Third experiment. What Faraday did, in third experiment, he again took a coil here, connected the galvanometer G, took another coil over here, connect the battery over here and used a switch over here. This is symbol of a switch. Used a switch over here. This time Faraday did not move this coil B or coil A. No. What he basically did, initially this switch was open. When this switch is open, there will be no current through this coil. When there is no current through this coil, magnetic field produced here is 0. So there is no magnetic field over here. Similarly, this galvanometer did not show any deflection. Then what he did, he closed the switch here. When he closed the switch over here, is the circuit complete or not? Now this circuit is complete. When this circuit is complete, current I flows in this circuit, coil B. When current I flows through coil B, this produces a magnetic field. It was found out that this galvanometer G showed deflection. Though current was flowing in coil B, but galvanometer connected to coil A showed deflection. That means there was some current flowing through coil A as well. How could you explain all these things? We'll come to that in next class, inshallah. Next, what he did, when the switch was closed now, switch is closed. Initially, when the switch was closed, this galvanometer showed deflection. Now the switch is completely closed. This is closed now. When the switch is closed, this is not showing any deflection. This showed deflection only when the time instant you close the switch. When you close the switch, this showed deflection. Now switch is closed, this is not showing any deflection. Next, what was done? The switch was opened again. When the switch was opened, this again showed deflection. This switch was opened and this again showed deflection. What does this mean? Then when this is open completely, this is not showing any deflection. That means this galvanometer is showing deflection only when this switch is being closed or this switch is being opened instantaneously at that instant only. When this is closed, this is not showing any deflection. When this is open, this is not showing any deflection. This is showing deflection only at that time instant when this switch is closed and that time instant when this switch is open. And how do you explain all the three phenomena, all the three experiments? How do you explain the three experiments? The three experiments were explained on the basis of laws of electromagnetic induction. That will come study next class, inshallah. If you have any questions, any queries, you can contact me on WhatsApp. Thank you. We'll continue tomorrow, inshallah.